Hello and welcome back to Mad Scientists. Hopefully, you guys are all here to learn some really cool stuff today. We will be talking all about fire. So, just like before, this is already getting warm with these candles over here. If you're watching live and are a student at a middle school, please write your name in the chat so we know who you are and who's tuning in. And besides that, I think we're ready to go. Today's follow-along experiment will require some kind of large container, big enough to really keep a candle in it, that's big enough to put stuff in it. So you can see the size difference there. So if you have a bigger candle, a little bit bigger containers needed. And then baking soda and vinegar. And really, that's it to talk about for our homemade experiment. So if you have that stuff ready to go, awesome. If not, now's a great chance to run and grab that. But we'll be talking all kinds of stuff about fire today. So fire is really cool to a lot of people, and it helps keep our world safe and healthy, which is kind of weird to think about because normally we think about fire being destructive and damaging and harmful. But really, fire is a good thing in nature because fire will go in and clean out old dead stuff like trees and bushes that are dead and no longer living. It'll go clean those up. It'll make the forest healthier because new plant life can come in. It'll actually be good for the wildlife because those different plants and flowers and berries and stuff like that do grow better after a wildfire. So fire isn't bad in nature. And just like in nature, fire isn't bad in chemistry. It has a lot of really useful applications. One of the most useful applications we as humans use almost every single day is the idea of combustion, which is burning something to make our cars go. Right? Our combustion engine is how all of our vehicles work. And the way that works is it takes gasoline and it ignites it and it expands and explodes and it creates a motor to turn. So we're going to talk about, before we get into the fun demos, I just wanted to quickly go over what is required of fire. I'm going to adjust the camera a smidge while I write. Okay. So, fire requires three things. So, right now, be thinking of the things that you think fire needs. If you want to pause this video, if you're watching it on YouTube, now's a great time to do that and talk about it. But fire needs three things. The first thing is a fuel, right? And that can be wood that's burning in a wooden stove. It can be sticks and stuff like that out in the forest. Or it can be things like gasoline. Something that these all have in common is they all have carbon and they all have hydrogen. So most fuel for fire are things called hydrocarbons, which are big long chains of carbon and hydrogen all stuck together. Sometimes there's other things in there, but the main thing is carbon and hydrogen, and that's what makes a good fuel. And then the other thing we need is oxygen, which, lucky for us, is in the air, right? We breathe oxygen, it's in our atmosphere. So it's really easy to find. That's why things burn so well on Earth. And that's why things would not burn very well on Mars, where there's no oxygen in its atmosphere, or very, very, very little, right? So, fuel and oxygen, but right now, you can see, like, here's an example. I have this wooden splint. It's just a wooden stick, right? This isn't on fire, but it's made of hydrocarbons. And there's oxygen around, so why isn't that catching on fire? Well, the answer to that question is you need an ignition source or a spark. So, ignition. Right? So you need a spark of some sort in order to make that happen. So, this is not, yeah, here we go. So to make that ignition happen, in order to burn things, you need that ignition source. And then once you burn this, you create two things. So here's our three things: a fuel, oxygen, and an ignition source. And what it generates is carbon dioxide, CO2, plus water, H2O. So carbon dioxide has talked a lot about, for climate change, greenhouse gases. That is carbon dioxide. We've talked a lot about carbon dioxide in this series, and we'll be using that as an example later on today as well. And then water, which is kind of weird to think about, right? When you're talking about fire, fire makes water. Like, it seems weird, but it really doesn't. But because it's being made by that burning of the fuel, what happens is it's water vapor, or kind of like steam. So instead of like little water droplets, it'll be water vapor, and it'll float off. So a campfire doesn't get really soggy and wet just because you're burning something. Otherwise the fire would go out. But it goes up into the air and floats away as a water vapor. So we'll be exploring a lot of this today. So we'll keep referencing this, but just as again, to go over it again, you need a fuel and oxygen plus an ignition source in order to make fire. And when fire is made, you produce carbon dioxide and water. Okay, now let's get to the fun part. Yeah, tilt the camera back down so you can see stuff. Okay. So, So I think what we'll do is we'll start off with the home experiment first. And then we'll go into the really cool stuff and why I have so much stuff on my desk right now. So I'm going to scooch this out. So here's our candle, right, that we're going to be using for our home experiment. I'm going to move our other demo candles over here for now. So for our home experiment, we'll need our candle and our container. And what we're going to start off by is just, oh, I forgot my spoon. So this one, definitely you can do at home. Just make sure you have a parent or a guardian to help, because we will be lighting this candle, but that's about it. So what we're going to do is we're just going to sprinkle some baking soda in here. 2 to 3 tablespoons is fine. Like, enough to cover the bottom is really a good measure. So you can see I got a decent amount in there. And what I'm going to do is I'm just going to shake around to get a good even layer. We want most of it on the side. So once we get a good layer, we're going to clear a space for our candle. And we're going to put our candle right in there. So it's kind of hard to see through this container. In fact, I'm going to get a glass container so you can see this a little bit better. I thought that would show up a little clearer than it did. But it's okay, I got a glass container right here too. So if you remember, the thing that we've been talking about a lot recently is carbon dioxide, right? So when we mix baking soda and vinegar together, it's going to create carbon dioxide. And remember, one of the things that we need in order to make fire happen really, really well is oxygen, right? Oh, that's a good angle. So we're just going to light this candle. So we have it surrounded by baking soda. We're going to light this candle. Let that get going for a little bit. So we need oxygen, right, in order to have a fire going. Right now it has all the oxygen at once. Speed this up just a little bit. It's a fresh candle, so it takes a second to start. Here we go. So because it needs oxygen to start, or to burn, if we take away the oxygen, this will extinguish the flame because there's no more oxygen. So we're going to basically create a fire extinguisher by combining baking soda and vinegar and creating carbon dioxide. So we don't even need, oh, there it goes. See, we don't need it to actually touch the candle because it created, and see, I can't even light this right now. There's so much carbon dioxide. It just goes right out. I can show you with the splint as well. So we'll get our wooden splint burning. We'll talk about this more in a second. The other direction. So here's our splint. If I try to put this in here, it just goes right out. It doesn't matter because there's no, what we're doing is we're taking away the oxygen it has. So it can't keep burning because there's no oxygen. You can see once it comes back out. So in here there's no orange, and then up here there is orange on that. So, and again, that's because it needs that carbon dioxide. It needs that oxygen in order to keep burning. So another cool thing you can do is you can pour this. I'm going to use what we have left over. Put this into our cup. Hello, new viewers. So again, I'm just going to pour some baking soda and vinegar together. It's going to create that carbon dioxide. And carbon dioxide is heavier than air. You can hear it bubbling. But what I can do is I can now pour this out, and I can put out this candle. Right? I can pour out the carbon dioxide, and it extinguishes the candle. Let's see if I can get a little bit. So I'm not pouring out any water or liquid. This is just the carbon dioxide extinguishing that flame. So this is an example of a carbon dioxide fire extinguisher, right? It's putting out the fire by removing the source of oxygen, and that source of oxygen is in the air. So, if we have oxygen in the air, why doesn't it just like explode, right? Well, it's because a couple reasons. One, oxygen isn't igniting. It's a part of the process of burning. And there's not enough oxygen to just ignite because most of our atmosphere is nitrogen, which does not react at all. So our next experiment is we're going to take this same, well, actually, we're going to use the bigger candle for this one. And try not to burn myself. Sweet. Okay, so now, where's my water? We're just going to pour some water in here. Right? That's just on a plate, so it's not putting out the fire because it's not touching the flame. And now what we're going to do is we're going to add some food coloring so we can see this water better because we're going to do a cool thing with it. Okay, so there's our food coloring. Just going to mix that up. So I used green food coloring. Again, the candle's burning just fine. And what we're going to do is, remember, flame, uses oxygen, right? So if I go like this to our cup, this is just an empty cup. If I go like this to our cup, it's full of air. Now, if I were to do this over top the candle, what do you think is going to happen? So what's going to happen is that fire is going to consume or eat up all of that oxygen that's in this cup, right? And then once it does that, it's going to condense the air in there because now it's used up all the oxygen and turned it to carbon dioxide or water vapor. So the water vapor is going to condense all along the side of the glass because the glass is cold and the vapor is hot. So when it touches something cold, it turns back to a liquid really fast. So when we do this, let's see what happens. So it's going to just keep going for a little bit. And you can see that water level is rising. And it fills our cup through that suction action, the capillary action. And now our cup is completely filled. And I'll move this around a little bit. So you can see there's some smoke in there. And our water is far above the level of the plate. So when we take this out, and our candle's floating actually. So now when I take this out, and you can see there's no more water actually on the plate. It sucked it all up. You can see there's our candle, right? So that's because it created a vacuum inside this cup, and it sucked up all that water as that oxygen disappeared. So now I'm going to dump this so we don't make a mess. Oh, I made a mess in my sink. That's okay. Okay, just so everybody knows, safety first, right? I have a fire extinguisher here, and I have a bag of sand underneath in case we catch any fires. We'll be safe. Safety first. So I'm just going to clear off. Okay, some other really cool, quick experiments that we can do. And again, these are a couple things you can do at home, but absolutely with parent permission and supervision, because these can be dangerous if you're not careful. So again, be very, very careful when doing these at home. But I just learned about this one this morning, and I think this is one of the coolest things I've ever seen. This is just a tea bag that I unfolded and then cut in half. So we're just going to go like this and then light it so you can see it on the close-up, but what you're going to want to do is watch above it as well. And I have a few of these so we can do a couple tests. It floats away. It's now like touching the ceiling. And it's going to fall really, really slowly. Here, you can see it hopefully on the camera right in front of me. There we go. It's just floating back down really slowly. And I'll see if I can bring this close to the close-up camera. Oh, I dropped it. Here we go. So that's all that's left over. Just this little tiny thing. So, again, all you have to do is cut a tea bag in half, empty it out, and then just stand it up. So the reason this floats away, and we'll leave two at a time this time. The reason this floats away is because the hot air of the fire, right? Fire is hot. Hot air rises. So when hot air rises, this becomes so light that it, all that hot air, that, oh geez, don't go into my plants. All that hot air forces it upward because that tea bag is so light. All right, I'm getting ash everywhere. I'm gonna have to vacuum later. Oh, hi, Alex. Glad you were able to make it. So that hot air makes it float up all on its own because the tea bag is so light once all of it's burnt away, and just that little bit of ash is left behind. So another easy one to do at home. Again, make sure you have parent permission and help. This is just alcohol, rubbing alcohol. And this is a regular dollar bill. There's nothing special about it. Well, there is something special about it. I accidentally tore it in half and had to tape it. So, we have to be careful here. We're going to make some room. So it goes right up in flame, but the dollar bill, well, my table's on fire now. The dollar bill is just fine. And that's because the alcohol burns off way, way faster than the dollar bill ever has a chance to. So we can do that again. It gets kind of hot if you're holding it the wrong angle. But again, even though my table was on fire, I wasn't concerned because the same thing's happening on the table where, you can see even I'm on fire. And it gets a little warm if you hold it, but you can, the table's on fire. That's okay because it's just the alcohol burning, not the table. So be very, very careful. I recommend you don't do this one on your own. Get adult supervision, but it's really cool to do. So our next experiment, how are we doing on time? Oh, we got plenty of time. Awesome. So we saw the carbon dioxide put out carbon dioxide put out a fire, right? Now what we're going to do is see what happens when you introduce oxygen. So we talked about this last week, this exact experiment, but this is hydrogen peroxide, and if you remember, hydrogen peroxide has one extra oxygen compared to water. So it's water with an extra oxygen attached. And then this is potassium permanganate, which we'll be using later on today for an even cooler experiment. But this is what's called an oxidizing reagent, and it has its own oxygen. So if you remember, where'd my whiteboard go? If you remember, we require fuel and oxygen for fire, and it creates carbon dioxide and water. One thing you might ask is why does the carbon dioxide that it produces not put out the fire itself? Well, there's kind of two answers to that. One is it can if there's not a way for the carbon dioxide to get away. And two, it gets heated up on its own, and the carbon dioxide will float away just like the water vapor does, so it doesn't sit there. So this is hydrogen peroxide, which has its own oxygen. This is potassium permanganate, which is going to make it release oxygen, plus also provide its own oxygen. So we have a lot of oxygen going on here. So when we combine these two things, this is like bright purple. When we combine these two things, it turns brown, which isn't very appetizing, but we're not eating chemicals. I'm going to relight my test candle. Okay. So now this is full of oxygen now. It just released a whole bunch of oxygen. So when I light my wooden splint again, remember this got extinguished in the fire, or in the carbon dioxide. So now I'm going to put it out. So we just have the orange, right? So there's no fire. Close up, there's no fire. And then I'm going to lift this camera a little bit. So when I put this in here, it restarts. You hear that little pop too? I'll move this up so you can see. So, no fire, put it in, it reignites, and there's a little bit of a pop. Pop! So that little pop is that quick ignition. I don't know if can you guys hear the pop? I'll move it a little closer. Pop. So this is full of oxygen, and oxygen is required. And you can see that it actually burns brighter. So out here, orange flame, right? I can hear awesome. So orange flame, and then when we put it in here, it's like a bright white, really intense flame. That's because the more oxygen there is, the faster things burn. And the faster things burn, the brighter that color, the more intense that color is. Oh, good. I'm glad you're able to hear that. So I'll just... Oh, no. Camera fell asleep. One moment. Sorry, guys. My camera fell asleep for some reason. So again, this is almost out just because I was just messing with the camera, right? If I put it back in here. Oh, we need a little bit more. Oh, we actually need more hydrogen peroxide. It's usually the other way around. So now you can hear it fuzzing and bubbling. Yeah, it went all the way out this time. That really intense yellow, bright white flame. So that's what happens when you provide more oxygen instead of more carbon dioxide. So now I'm going to set this off to the side. We'll be looking at a different experiment with potassium permanganate later, which is what that was. So now one of my favorites. Well, actually, there's one more thing we should. Oh, actually, two more things we should talk about. So here I have two balloons. This first balloon is filled with water. It's like kind of a water balloon. It's mostly air with a little bit of water. This one, just air. So one really cool thing, what do you think is going to happen when we put this yellow balloon on top of a flame, right? It pops really explosively, like all of a sudden. And that's because it's melting the plastic. And I put out my candle. It's melting the plastic of the balloon, and it made it go away. So one really cool thing you can do is, since this has water in it, I can put this over here. I'll do this on the close-up so you can see the reaction. I can hold this. I can even touch the fire with the balloon. Did a little too much. But you see, we were able to hold that there for a lot longer. I'm going to get a towel so I'm not making a mess in my living room. But like I always say each week, if you're not making a mess, are you really doing science? But we were able to hold that there for a long time. And if we have time, I can go back to this one. But because that water was there, and it was absorbing all of that extra energy of the fire, so it wasn't able to melt the plastic. If I were to do this, if we do this again, I'll fill the balloon all the way up. That way we don't have to worry about any non-water parts touching and popping. And I think that's what happened here. So you can hold a balloon. Oh, cool. It like blew the wax away. In the melted wax from the candle. So it melted the little non-water part. So for this next part, I'm going to turn off some of these lights so we can see the fire better. And hopefully my camera works all right. I'm going to get as dark as we can in here. In fact, I'm going to even block out this other window with a blanket just so we can get a really good view of this fire. Okay, one more thing to block off, and then we're ready to go. Okay, it's at least a lot darker. So the reason we're doing this is because this next thing involves color of fire. So here I have methanol, which is a kind of alcohol. It's not the same alcohol that are in like the kind of alcohol you drink. It's not the same kind of alcohol that's in rubbing alcohol. It's a different kind of alcohol. So all I've done is put this in this metal bowl. And I've chosen this metal bowl for a couple reasons. One, it is heat resistant. And two, it won't melt. Because we're going to be lighting this on fire. And let's get a better close-up view of this. There we go. That's pretty good. Fire, right? Not crazy interesting. You've seen fire before, but still fire. So, remember, I have my fire extinguisher. I have my sand, so we're safe. I have all of these different chemicals in spray bottles. And you might ask, why would I ever do that? And you're about to find out. And it's because these chemicals, and they're all different kinds of metal salts. Oh, there we go. These chemicals change the color of fire. And hopefully that's showing up on camera, as well as is in person. Let's try a different color. That one was like red. There's more intense colors. This one's like white-ish. We can do better than that. There we go. That one shows up. Green fire, right? So, how many times have you ever seen green fire before? This one's like red. You can see there's some green tinges to it. That's because there's some leftover chemicals from before when I sprayed. This one's also green. Or is this one red? See, it's hard to tell because we're getting a mixture. And then this one should be blue. Oh, this one's also green. That's right. So, different colored fires. And the reason this works is because these different salts, these different metal salts, I'm going to blow that out for now because it's really warm. These different metal salts get excited. So you start it at low energy, what's called your ground state energy level. So it's like a regular energy level. And then the fire adds a bunch of energy to it because it's hot, right? So that fire adds energy to it and it excites those molecules. And when those molecules are excited, they say, hey, I have too much energy. I want to get rid of this. And then it gets rid of it by releasing different colors. And those different colors are what we see. So because it's releasing those different colors, in order to get back to that ground state, that lower energy level, it says, hey, I have too much energy, let's get rid of it. Bam, we're going to get rid of it via color. So that's why that happens. So, you can hear this is really hot. I'm going to relight this. There's one more thing we can do. And if you have any questions, please feel free to ask them at any time. We also have these iron filings, which cause sparkles. And those sparkles are the iron just burning on its own. So maybe if we're fast enough, we need more alcohol. It's getting because these salts are mixed with water. The water kind of gets to the bottom of this, so we burned off a lot of alcohol. So we're just getting a little bit more. Well, that's cool. Let's see if I can get you to look right down into it on the close-up. See those little sparkles? Okay. We're going to go for green sparkles. Here we go. I think we have a better green. There we go. That's a better green. So we're going to do sparkles at the same time as green. Awesome. I love this so much. It's so colorful and fun. So, so that's our colored fire experiment. And now, I'm going to readjust. This has to cool a little bit. You can hear it's super hot. So while that happens, we're going to do one more experiment in here. And then we're actually going to go out to my porch. I have one last experiment to do on the porch that produces a lot of smoke. That's why it's outside. And hopefully my camera should be able to mix or make it out there. So our next experiment, I'm going to zoom out a little bit, bring this over. There we go. So we have this graduated cylinder. We're going to put some alcohol in here. And we're going to just mix it up. So we want this alcohol, this is rubbing alcohol this time. We want this alcohol to evaporate. The reason we want it to evaporate is because when it evaporates, we get that alcohol vapor. And because alcohol can evaporate at room temperature, right? So we fill this with alcohol vapor and then light it on fire and see what happens. Catch it? We can do it one more time with this one. We have a couple more containers to test out. So again, we want that vapor. It goes pretty quick, so you'll got to watch carefully. If you're watching this on YouTube, I recommend slowing down the speed on the settings, and you can watch this in slow-mo. Come on. It's just burning the top for some reason. I don't know if you can see this at all. It's like just on the top layer and slowly making its way down. Oh, it went out. I think there's just what's left behind is water, and that was the liquid I was swirling around mostly. So again, we'll do this one more time. Can we see it? All right, here we go. Maybe there's a better angle with less glare. I'm trying, guys. There it is. So not super exciting, but we can make this more exciting. Okay, so the way we make this more exciting is we use a bigger container with a narrow top. So we're going to put alcohol in here, and again, we want this to evaporate all on its own. So we're going to swirl this around. I'm going to plug the top with my gloved hand, and we just want as much of this to evaporate. So we're going to swirl it around probably for like a minute or two. As much as we can, we want to get as much of this evaporated in the container as possible. I'm getting some on my hand, but that's okay. So we're going to fill this up, and then because it has that narrow top, it's trying to force that out really, really fast through that narrow top, and it makes that whistling sound. And you can see it's actually still burning in there for a little bit. There goes the last little bit of it. So now we can do this again just because that sound is so much fun. And it's warm this time, so it should go even faster for that evaporation. So we'll just swirl it, swirl it, swirl it. We want as much of that evaporate in the container as possible. And you can kind of tell it's done when you can kind of smell it. That means it's been evaporated. Okay, here we go. I'm going to tilt this up a little bit so you can see the top. I was not going to do it just like before. So I think what we need to do is there's no more oxygen in here. That's what's happened. So what we're going to do is we're going to dump that out. Blow into it. Oh, yeah, you can tell there's a lot of stuff in there. Okay, now that we've added some oxygen back in there, we'll do this again. So you don't need a lot of alcohol because we just want it all to evaporate. We don't care about the rest. We don't need any liquids, really. So we just want it all to evaporate as best we can. Shake it up, shake it up. And then oh, you just worked. Why are you not going to work? Oh, it's starting to go. maybe. I don't know what's going on. Oh, well, we got to see it once. I think it just needs to sit and relax. So we can revisit that one after we do our next and last experiment. So now I'm going to take you outside. I'm going to turn off this camera for now. I'm going to switch to the close-up. And I'm going to set you outside so you can see this, and then I'm going to come back in and make sure that it's all looking all right before we actually do the experiment. There we go. Going outside. Hopefully the cord's long enough for all of this. It's really nice out today. Again, feel free to ask any questions. Okay, I'm going to go back inside and make sure that this is looking all right. Yeah, good. Wow, that looks really good. Okay, so remember I told you we were going to look at potassium permanganate again. So, potassium permanganate, we're going to take this and we're going to, oops, I had a seal on it that I just broke. So we're going to take our potassium permanganate, and remember, this has a lot of oxygen already bound to it. So it has its own oxygen supply. In addition to the oxygen supply we have in the air, right? So what we're going to do is we're going to combine this with a fuel source. And this fuel source is glycerol, which is basically just plant sugar. So this one takes a second. So we're going to pour our glycerol on there, and now we just wait. I know it doesn't seem like anything super exciting. I'm going to move this stuff out of the way. I'm going to go back inside to make sure that we can all see it. But we just have to wait, and you'll start to see some of the reaction. Oh, there it goes. So it just starts steaming it. Oh, and there's the fire. Yeah. So we just created fire out of a liquid and a solid. And you can see there's some gas, and this is why we did it outside. It's also very hot. So I'm going to just lift this a little bit so it doesn't melt my tablecloth. But you can see, I'll see if I can get you a little closer too. That's about as close as I can get you. It kind of looks like lava, and it's hard to see in the sunlight, but it is still definitely burning. You're going to go back inside and make sure you can see everything. Good. Okay, so we were just able to create fire from a solid and a gas, and I'm going to just leave this outside because it's going to be hot for quite some time. But what we can do is I'm going to go get one of my wooden splits. What we can do is this is actually also turned to a solid. So it's completely solid now. Oh geez, there's some left over. So this is actually probably going to react again. In fact, there it goes. It's already reacting again. Because there was some stuck underneath that didn't react. So I'm going to, oh, and there it goes. It's going to create another fire. Awesome. This stuff is so cool. I love this so much. And there's the fire. Oh, it's very smoky. Glad we did this outside. So I'm just going to let that burn and take us back inside now. Whew. There we go. My eyes aren't adjusting very well. Okay. Just pulling up our other camera. Why aren't you being recognized? Oh, got unplugged, that's why. Oh, well, you can see me now. See my setup. Just setting this up to say, okay, live shoot. There we go. Okay. That's all the fire experiments I have for you today. If anybody has any questions, please feel free to ask. Again, just to recap, right? Fire needs fuel and oxygen. It produces carbon dioxide and water, and you also need an ignition source, a fuel source. So one kind of crazy thing that we just saw out there is we actually didn't really have an ignition source. So how did we get fire? And the way that worked is, remember, those two things reacted together, and it produced its own oxygen, and it's what's called an exothermic reaction, which we talked about before the last 2 weeks as well. So that exothermic reaction means it's putting off its own heat because it's going through that chemical reaction. And it actually produced enough of its own heat to catch on fire. So it's then on fire all on its own, and it's able to ignite. So it's its own oxygen source and its own ignition source. And then the glycerol, the plant sugar, is its own fuel. So it's all contained, and that's why it was a liquid and a solid that was able to make fire, which I just always thought was so interesting. We looked at, I wonder if this is cooled down. It's cooled down a little bit. We looked at different colored fire. Remember, that's based on the amount of energy that those different salts like to get rid of. And then we looked at a lot of different ways to burn alcohol in different containers. And I wonder, we do have a little bit of time. I wonder if we can make this guy work again. Just because I love that pop. We'll just swirl this around while we finish talking about this stuff. But again, we also looked at making carbon dioxide fire extinguishers using baking soda and vinegar to produce carbon dioxide to extinguish a flame. And we also used potassium permanganate in order to, and hydrogen peroxide in order to make oxygen. And then we saw the effects of adding extra oxygen to the system as well. So, lots of different things we looked at. We lit a dollar bill on fire, and it was just fine because we just burned the alcohol that was on that dollar bill. We sucked up water by creating a vacuum with a candle inside a cup. That's something you can do at home as well. And those were kind of most of our experiments. Oh, we also looked at iron filings being burnt. The reason I used methanol, that other alcohol, instead of rubbing alcohol or drinking alcohol is because that methanol actually has the least amount of color on its own. So we can see the colors of the metal salts a little bit better. Okay, I have a feeling we have a good amount of vapor in there now. Let's see what happens. I want you to see the top of this on the close-up cam if you can. Yeah, there we go. Still doing it. I don't know why it worked the first time. Well, if you want to see it again, you can rewind and see what happens. Oh, maybe we'll go. Nah, it's not working. Oh well, we had a good pop the first time. So, if you have any questions, feel free to leave them in the comments. Love to hear from you. We'll be meeting again next Friday at 3 o'clock, same time. And next week we'll be looking at liquid nitrogen, I believe. So, lots of cool stuff. Come back next week. We'd love to have you, and have a great rest of your day. Bye.